And
hello, Zhang.
Can you hear me clearly?
Hello, Menji. Hello, Menji.
Hi.
Would you please mind if we read
Hello,
out your...
can you hear me?
Hello, can you hear? Can you hear? Hello?
I can hear you.
Yeah,
Can
they
you
need
hear
to
me?
introduce you.
Yeah. This is one
Okay.
formality.
Okay.
So, would you please mind to stop for a while so that we can introduce with your latest biography? Please allow us. Okay. And then
Okay. Thank you.
okay, please bear with. Okay. Tandradi.
Yeah.
Tandra Pal, are you here?
Yeah. Yes.
Please. She
Okay.
happens to be our chair of Computational Intelligence Institute Kolkata chapter. So let us speak out your biography. Okay, it is biography.
Okay. Thank you, Paramatso. Good morning to all of you. It is my honor to introduce M.Zhang to all of you. M.Zhang is a fellow of Royal Society of New Zealand, a fellow of IEEE, an IEEE distinguished lecturer, currently professor of computer science at Victoria University of Wellington, where he heads Hello, Paramartha, mute yourself. Yeah. He heads the Interdisciplinary Evolutionary Computation Research Group. He is a member of the University of Academic Board, a member of the University of Postgraduate Scholarships Committee, Associate Dean in the Faculty of Engineering, and Chair of the Research Committee of the Faculty of Engineering and School of Engineering and Computer Science. Main areas of his research interest are artificial intelligence, machine learning, and big data, particularly evolutionary computation based on GP, PSO, LCSD, and EMO, feature selection and big dimensionality reduction, symbolic regression and mathematical modeling, computer vision and image analysis, evolutionary deep learning and transfer learning, evolutionary clustering and visualization, evolutionary scheduling and combinatorial optimization, and bioinformatics. Professor Zhang has published over 600 research papers in referred international journals and conferences. He has been serving as an associate editor or editorial board member for over 10 international journals, including IEEE Transaction on Evolutionary Computation, IEEE Transaction on Cybernetics, IEEE Transaction on Emergent Topics in Computational Intelligence, ACM Transaction on Evolutionary Learning and Optimization, the Evolutionary Computation Journal of MIT Press, Genetic Programming and Evolvable Machines of Springer, Applieds of Computing, Neural Computing, and Engineering Applications of Artificial Intelligence. He has been serving as a reviewer of more than 30 international journals. As a chair, he has been involving major AI and EC conferences such as GECCO, IEEE CEC, EvoStar, AAAI, IEEE SSCI, and many more. He has also been serving as a steering committee member and a program committee member for over 100 international conferences. Since 2007, he has been listed as one of the top 10, currently number 4, world genetic programming researchers by the GP bibliography. Professor Zhang is a past chair of the IEEE CIS Intelligent Systems Applications, the IEEE CIS Emergent Technologies Technical Committee, and the IEEE CIS Evolutionary Computation Technical Committee. A vice chair of the IEEE CIS Task Force on Evolutionary Feature Selection and Construction, a vice chair of the IEEE CIS Task Force on Evolutionary Computer Vision and Image Processing, and the founding chair of the IEEE Computational Intelligence chapter in New Zealand. So I welcome and also request Professor Menji to start his distinguished lecture.
Thank you very much for your nice introduction. And it's my pleasure to give a talk and in a special format of Zoom and in Calcutta chapter, new chapter. And I was asked and to give a talk in the area for evolutionary machine learning. And this is actually a very big topic. It is not possible to give a lot of details in specific areas. And so I would like to give some overview on machine learning and evolutionary computation, and then some specific overview on evolutionary machine learning on classification, feature selection, and regression modeling, clustering, and image analysis, combinatorial optimization, and evolutionary deep learning. And in particular, depending on the time, and I might give some examples on and how to evolve deep neural networks and how to use genetic programming for image and vision processing. At the end, I'll give some topics on the challenges and applications. And what is AI and machine learning? And these days, many people think, AI is actually CNN, convolutional neural networks, because these days, CNN is so hot. And if you check the top international conferences on artificial intelligence and machine learning, you will find that more than 70% of the papers are using a different kind of or variant of CNNs. Some people think AI is machine learning, and machine learning actually is deep learning, and deep learning is deep neural networks, and deep neural network is CNN accordingly, and AI is CNN, of course. And this is not correct. But from application point of view, and many people think in this way. As I mentioned, those top AI machine learning conferences, actually, they think, and there are a lot of papers published and using topics in CNN. Okay? And in fact, the evolutionary computation people clearly do not like that idea. And of course, they have very good reasons on that. But from a general view in the area for AI and machine learning, and we should not say AI and machine learning, they are CNNs. That CNN is only one of the aspects. Right? So this is only one of the aspects. And here, we give a very popular view on AI and machine learning, 5 points. Of course, this is by Professor Deborah and Domingos. If you look at it, they split the whole AI and machine learning areas into 5. So the first one is actually symbolic AI. Like you can see, that's symbolic AI. And then that's connectionist AI. Connectionist AI mainly neural networks and gradient descent, based on the slope of the cost functions. And then the evolutionary AI, evolutionary learning, that's mainly the genetic search and genetic paradigms. With a moment, we will see this in more detail. And then the Bayesian method, that's based on the probability stuff. That's a large chunk of machine learning. And this side, that's based on the kernel machines, the kernel method. And like typical example would be support vector machines. And in general, the AI and machine learning, particularly machine learning, at least have the 5 paradigms, right? You can see neural network, that's a big one, and evolutionary computation is the bigger one, and the probability-based a bigger one, and the kernel-based a bigger one. So these are traditionally, we can say that's the computational AI, and all actually, that's the data and driven an AI machine learning method. Of course, the old is, when AI was established in 1956 or 55, basically, like Professor John McCarthy and those people, and they are symbolists, right? The symbolic AI people. That's still based on logic and computation, logic and philosophy. There's still a lot of research there. Okay? But today we are mainly talking about the computational side, this side. Okay? And come back to this paradigm. This is AI machine learning. This is major paradigm called evolutionary learning. The term evolutionary learning or evolutionary computation, in my view, and has at least those three big categories. One is based on the so-called evolutionary algorithms, and another one is swarm intelligence. And then if any paradigm or techniques cannot be fit into these two categories, and then that's other. Of course, and people can have different opinions, but that's my own view. For the evolutionary algorithms, at least the old paradigms, powerful paradigms, genetic algorithms, genetic programming, evolutionary strategy, and evolution programming. So particularly GAs and ES and EP, they are the three oldest and EC paradigms. They discussed, this was invented in the 1960s and by three independent groups. And in the 1980s, later 1980s, people found that actually they share a very similar scheme called, and that's why people give a name in the late 1980s, early 1990s, called evolutionary algorithms. And meanwhile, and in the middle 1990s, 1995, and they say based on population and social intelligence, that's why called swarm intelligence. Typical examples would be particle swarm optimization, PSO, anti-colony optimization, ACO, and of course, and artificial immune system can be also come to other, okay? In this paradigm, and they have a lot of others, like artificial bee colony optimization, ABC, right? And there's many, many others here. So basically, we can roughly say evolutionary algorithms, all those algorithms are based on human evolution, which is actually based on natural selection, Darwinian natural selection, and gene theory. That's mainly mimic human evolution and then develop those algorithms. Okay? Swarm intelligence, on the other hand, and this also actually this based on some kind of evolution, but adds some social distance, social intelligence. This roughly we can say, and based on animals and evolution, like the bird and flying, animals, flying bird, or something in the water, fish, or something in the land like ant and or bee or something like here. So a major difference, actually, those two big categories, evolutionary algorithms and swarm intelligence, they have a common characteristic, which is population. So, and every time, every single experiment run for both evolutionary algorithms and swarm intelligence actually can find more than one solution, a population of solutions based on population based. But the individuals in the population in the evolutionary algorithms are relatively independent. They do not have interaction until the evaluation and crossover stage, right? So However, for the population in the swarm intelligence side, like PSO, and the individuals and in the population, they call swarm in PSO, they are connected. That's social intelligence. So they have some topology there. So this is a major difference, okay? And there are also many other paradigms, many other evolutionary computation techniques. They are not evolutionary algorithms. They are not swarm intelligence, but there's something other, like learning classifier systems and evolutionary multi-objective optimization, hybrid or mimetic algorithms are typical examples of this kind. Okay, that's the EC parallel evolutionary learning. Okay, and now we come to today's main topic, which is evolutionary machine learning. We have just done a very brief introduction overview on machine learning and also evolutionary computation. And then we have two categories of different views for evolutionary machine learning. Okay, the first one is a narrow view. I call it evolutionary learning. Okay, this and the evolutionary learning in this case, actually, that means using EC method, evolutionary computation method, including all those methods, and for different kind of learning directly, like genetic programming, learning classifier systems, and artificial immune systems. Those methods are actually evolutionary learning methods. They are optimization methods and also learning methods. Okay, this is a very narrow view. From that point of view, the EC in whole, including evolutionary optimization and evolutionary learning. And however, these days, majority of papers published on attribute transactions on evolution computation are in the area of evolutionary optimization. There are very few few papers are in the area of actually evolutionary learning. Okay. However, the pattern, the trend is increasing. And recently, actually last year, ACM introduced new transactions called ACM transactions on evolutionary learning and optimization. So that's mainly the evolutionary learning, and that's the focus. Okay, and basically this is a narrow view, and a broad view would be the narrow view plus any EC method for any kind of machine learning tasks, and including actually automatically find the parameter values and optimize the parameter values and other aspects, everything. So basically, this is a relatively broad view. So that's the two views. And I'm not going to say which one is right, which one is wrong. Actually, both of them are correct. It's just the one is narrow and the other is broad. Okay? And if you are interested, and you can have a look on this survey paper, that's our group, and jointly made a survey on evolutionary machine learning and in the Journal of Royal Society of New Zealand. And also they have the Royal Society of New Zealand, they publish a highlight on what can artificial intelligence learn from nature. Actually, that's a very interesting argument there, and you can have a look. In the next few slides, I'm trying to cover a number of aspects in evolutionary and machine learning. The first one would be evolutionary computation for classification and feature manipulation. Okay? So usually in this area, there's a lot of work has been done, right? And in terms of classifier construction, how to build a classifier for different tasks, right? And in this case, and traditionally, the genetic algorithms and PSO, they use vector, actually fixed length vector representation. And in fact, and if you use GA plus reinforcement learning, and then that would be learning classifier systems, okay? Learning classifier systems has different kinds, and a popular, very popular scheme is XCS, and this is for continuous learning or online learning, and it's not necessarily supervised. UCS and these paradigms of classifier system, in fact, is supervised learning, okay? But recently, and people have already extended the traditional learning classifier systems by using code fragment, which is actually a part of GP trace. GP means genetic programming. Compared with GAO PSO, which use a fixed length vector representation, and GP typically use a variable length and tree-based representation. However, the tree-based representation and is actually the most popular one, but it doesn't mean it didn't have other representations. In fact, GP and genetic programming can use the tree representation, which is the most popular one, but can also use a graph representation, grid representation, grammar representation, and any other models or computer programs and irregular representations that's actually in GP. Okay? This is a very powerful scheme. And wait a moment, if I have time, I'll specifically provide some concrete examples there. And artificial immune system, that's another major paradigm in evolutionary learning for different kinds of classification and other machine learning tasks. And when building or constructing classifiers, unbalanced data set and all class imbalance problem is also important aspect. For example, in the medical domain, the number of patients or instances and who are actually patients who actually with disease is small. The normal people and is actually a lot. They have a lot. So for a medical and disease diagnosis data set, it is often the case that the number of patients is very small. The number of people without disease is a lot. So you can see that's highly unbalanced. If we use the normal and machine learning or evolutionary learning method to solve, the model often biased to the majority class. Another area is actually missing value. Sorry. The missing value means that in the table, actually, and in the data set, some value were missing. Some of the machine learning algorithms can directly apply to data sets with missing value, such as CART decision trees. But many of them cannot, and we need to develop machine learning methods, including evolutionary and machine learning methods, to do that. And we have two different directions. One is that, some values are missing. Let's amend that. That's so-called using imputation method. impute those meeting values with based on the current values, and then using every every machine learning method can solve the problem. Okay, another one is direct develop classifiers that can deal with the data sets with meeting values. These aspects also have a lot of research there. So another major direction in evolutionary machine learning is actually feature selection and construction. And in this area, there are a lot of work has been done. And we will discuss that in terms of evolutionary paradigms here, or evaluation criteria, or the number of objectives. And this actually, and 5 years ago, and we published a paper that's a survey on evolution computation approaches to feature selection. And this is one of the most popular papers on attribute transactions on evolution computation. This morning I had a look, and this is the 3rd out of 50 popular papers in this journal. Okay. In terms of the EC paradigms, and we can see actually typically they have both genetic algorithms and genetic programming are used actually for feature selection, and swarm intelligence. There's many methods, but typical ones would be particle swarm optimization and anti-colony optimization. Okay, there's also other EC paradigms, mainly differential evolution, mimetic computing, and others. Okay, and in terms of the evaluation criteria, and some of the evolutionary feature selection methods, and using filter-based approaches, some of them using wrapper-based approaches. Wrapper means that during the evolution learning process, they wrap a machine learning algorithm or classification algorithm. The evaluation of the goodness of the features are based on the classification accuracy. But the filter method, on the other hand, they do not wrap any classifiers. Instead, they try to get some useful but low computational measures like information gain, information theory methods, from information theory, or from other statistical methods. That's simple. Typically, because of not wrapping any classifiers, filter approaches are often faster, but the wrapper approaches are often more accurate for that particular classifier. Okay? The combined or hybrid approaches combine the advantages from both wrap approaches and filter approaches. Okay? And the filter measures, I mentioned a few actually, include the information theory measures, correlation measures, distance measures, consistent measures, fuzzy set, and rough set. Okay? Basically, we have done every category except the fuzzy set. We haven't done much on that. So details can be seen from this paper. The next big category for evolution machine learning is regression, using EC method for regression. Regression means, this is another name and modeling or model identification. Okay? You want to find the relationship or mathematical relationship between the output variable and the input variables or features. Okay? You don't know, right? And traditionally, there are two ways to do that. One way is to use a statistical regression method. So basically, we have the data, we analyze the data, and we analyze the data, and we find out the closest distribution. Based on the statistical distribution, we choose a method, and regression method, and then an regression model. From the model, and the model is fixed. The only task become actually we find good parameter values. So this is the parameter estimation. From that, you can use a lot of statistical methods. On the other hand, you can also use actually many of the EC methods, evolutionary learning methods, genetic algorithms, particle swarm optimization, and differential evolution, and artificial bee colony optimization are popular methods. However, this is a big category. Most people are doing that. However, this method has the biggest disadvantage. Basically, people need to have good statistical knowledge. You need to analyze the data, and you need to find out which distribution the data follow. And actually, in these days, the big data era, right? The data is so complex that it's not possible to find a single distribution. In fact, many cases, this group of data could follow multiple distributions. And then using the above method, statistical regression or parameter estimation is very, very hard, actually. And to address this problem, we use as a second category, we call the symbolic regression. The symbolic regression, meaning that, and they can, and particularly the method actually is a genetic program. These can, remove all the assumptions on the data distribution and the data models. You don't need to choose. Instead, we use genetic programming to automatically and construct the model structure and the parameter values associated with the structure simultaneously. So this, and compared to the parameter optimization and or estimation methods, statistical and regression, symbolic regression remove the assumption of the data, remove the prior knowledge of using statistical method. So it's very good, actually. So this, and currently genetic programming is dominates this method, this domain. And learning classifier system, artificial immune system can also do that, but much harder. In fact, our traditional method, some method can also do that. A typical example would be decision trees, or actually random forest can do that. Okay? The next category of evolutionary machine learning actually is using EC methods for clustering. Compared with classification and regression, which are supervised machine learning methods, clustering is actually unsupervised machine learning method. In other words, the number of the class labels are not known in advance for any instance. So this is unsupervised. In this way, actually also, and people have done actually those ideas, have done those work. Say, although the class labels are not known in advance, right? And so, but the number of clusters is known in advance. And in this case, we say evolutionary fixed clustering, fixed number of clustering. Okay? The other one is automatic clustering. The number of clusters is not known in advance. Of course, this is much harder than the first category. Okay? And in addition, evolutionary clustering with bigger dimensionality. So many of those and data, particularly in biology and medical data, they have thousands or tens of thousands of features or dimensionalities, very hard. And then you can't really visualize it. You don't know that the features, the dimensionality is so high. However, using genetic programming, you can reduce the dimensions from thousands of dimensions, 1,000 features, to 2 or 3 at a very small number. And you can say that, oh, the statistical t-SNE method can do that. That's true. However, t-SNE just do direct mapping. And every time you need to do from scratch, you don't really know the mapping models. Using genetic programming, you can obtain the mapping models. You can apply this model to the future unseen data. So that method is much advanced than t-SNE. Actually, one of my colleagues or previously my PhD student and postdoc, and published a paper in this area in EuroGP, and obtained or received the best paper award in 2019, actually. And a big challenge in this area is the lack of benchmark and data set, and also lack of evaluation criteria. Okay? This is still a big area. And University of Stirling, UK, they have done some work in this area. And I wrote a reference for them. They are applying for the best PhD dissertation award. Another big category is actually using evolutionary learning, machine learning method for computer vision and image processing. This is actually a big domain, big area, and including actually those at least three categories. Firstly, image pre-processing, like edge detection, segmentation, noise cancellation, image enhancement. Those tasks have been done actually using genetic programming and particle swarm optimization, genetic algorithm, and differential evolution. That's have done very well actually. Those tasks are relatively straightforward. Okay? Another big area is to use an evolutionary machine learning method for image feature manipulation, including feature selection we just discussed, and feature construction. Feature construction means that you already select or receive a number of important features by feature selection, and then you want to combine them together using different kinds of operators and to form high-level features. That's called feature construction. Of course, feature construction can also reduce the dimensionality. Another big category, and people have already done, is for text feature analysis and image descriptors. That's a lot of work has been done. There's a combination of safety feature, surf feature, and there's many other features, and all the image descriptors have been done. Those are relatively low level and use for evolutionary and machine learning methods. There's a relatively high level called image classification or object detection. So closely, there's this area, many people use and GP, PSO, and many of those evolutionary machine learning methods for template matching, salient object detection, and image classification. And there's a lot of work has been done. Wait a moment, I'll provide some examples in this area. Another big area is, in fact, is using evolutionary learning methods for scheduling and combinatorial optimization. When I mentioned combinatorial optimization, I really means that job shop scheduling, this is a dynamic scheduling, dynamic flexible scheduling, scheduling and routing, right? And arc routing and vehicle routing. And also in operations research and bin packing programs. And in our cloud computing or grid computing facilities, and we these days have been using, that's, resource allocation. This is an important method. In the website, web service combination is also a kind of combinatorial optimization. Traditionally, those methods, those tasks have been using and basically have been using an optimization method rather than machine learning methods to do. However, particularly for the dynamic problems or dynamic flexible problems in scheduling, routing, packing, combination, and resource allocation, this has become an NP hard problem. It's not always possible to find a solution using exact method or heuristic method. Instead, people are using hyper-heuristic method. Basically, genetic programming is dominant in this area. And when it comes to hyper-heuristic approaches, essentially, they become machine learning, evolution learning approaches. Another very important area is evolutionary deep learning, okay? Deep learning these days, when we talk about machine learning, if we don't talk about deep learning, and then it doesn't make any sense, right? But what is deep learning? Different people have different opinions. We know that the deep learning idea these days, most people say deep learning came from neural networks, derived from neural networks. In the old days, and in the 1960s, there's people called linear threshold units, only a unit or perceptron called neural networks. And in 1967, Professor Minsky from MIT University, they identified actually the perceptrons or linear threshold units cannot solve linear and known separable problems. And then because of that, they kill the AI, slow down the AI for the whole AI domain for 20 years until the mid-1986, when Ramahan and Jeff Hinton, they proposed parallel distributed processing. That book proposed the gradient descent and back error propagation algorithm. Okay? But in the 1980s, the neural networks, only 3 or 4 layers of nodes, only very small and number of hidden layers. But these days, and in the late 1990s, Ian LeQuinn has already expanded that to 5 or 6 layers. Okay, and later on, and in 2006, that's already actually over hundreds of layers, and now that's over 1,000 of layers. Okay, that's deep and deeper. Okay, so but what is and deep learning. And that's a deep model. Different people have different opinions. This is Professor Zhihua Zhou from Nanjing University, China. And he gave a keynote in EasyKai last year. Of course, that's virtual. But before that, when he visits me and in New Zealand, we have already discussed. I fully agree with this, actually. This is a deep model. But this need to have 3 features to call deep learning. Firstly, the deep model accordingly need a lot of training data, okay? And otherwise that's overfitting occur, right? There are a lot of tricks to train and needs GPU or very powerful computational facilities, okay? So this needs data. So accordingly, the model need to be sufficient complex. If too simple, and the model will not be able to eat the big training data, right? This is important idea. Another important idea need to have layer by layer processing. Okay, like here, the first layer, second layer, third layer, and so on and so forth. And the first layer and equivalent to some low-level features. Okay, that's like row features, and then this is a higher level features, higher and higher. So this need to have feature transformation between the layers. So the 3 conditions. The model need to be sufficiently complex, and then need to have layer by layer processing, and then need to have feature transformation. That's from Professor Zhihua Zhou's idea. And my own view, I fully agree with Professor Zhihua Zhou, but I extend it. I agree with the layer by layer processing. But the feature transformation need to include not only feature extraction, people normally say, should also include feature construction, what I explained earlier. And more importantly, can learn different representations. We call the feature learning. Okay? And recently, we just published a book on feature learning, okay, by Sprinkler. And last month it's just published. Okay? The sufficient model complexity is also important. But the complexity here doesn't mean or not equal to the number of nodes or number of layers. That's what most people are doing, most people are counting. It should include functional complexity. More importantly, should be actually not necessarily symmetrical, like the previous example. This is symmetrical. Okay, and also here the mentions need a large training data, but in many domains we don't have, like in medical domains, new disease, right? And like current COVID-19, they have some variations, and then people don't, at the beginning, they don't have enough instances or examples. And in addition, how about the interpretation? And this is only 1, 2, 3, 4, 7 layers. It's already very hard for us to interpret. But if we have 100 or 1,000 layers, that's not possible to interpret. Okay. In addition, here, this is a lot of disadvantages for neural network-based deep learning method. Okay? And there are too many layers, there are too many hyperparameters here, too many layers, and too many feature maps, too many nodes in each map. And those need to be learned. It's not an easy job. That's why I need a large amount of data. And also use typically stochastic gradient descent. We know that the gradient descent can only, to train the weights, they can only find a local minima, cannot find a global minima. And also, after learning, the model would be fixed. Okay? And if you slightly change to a data to some other data, other domain, and then you need to learn the neural network architecture and weight from scratch. Okay, so the black box and large training that data and theoretical analysis is difficult. Those form the major limitations of neural network-based machine learning. Okay. Having said that, this is a very popular domain, and majority of the deep neural networks are manually designed. Okay, the manually designed CNNs or DNNs, including the ResNet, DesNet, VGG, and many of those, and they are manually designed for specific image classification problems. Okay. Typically, they are done by the big companies like Google or Amazon or Baidu or somehow. They have a big group of people, have and 30 or 40 experts in neural network and also in the image application domains. And then they trial and error and run in large GPU servers. Okay, that's usually in most of the universities and research institutes, we do not have those resources at all. The question is, can we not actually using the manually designed way and use so many experts and the high computational GPUs or resources? Yes, and how about automatically design that? And evolutionary computation actually can play a major role in this area. Okay? I call it evolutionary deep learning. Evolutionary deep learning include actually two different categories at least. The first is actually neural network based. They also called deep neural evolution. Okay, typical examples would be the CNNs, also encoders, deep belief networks, and those GANs, right? And also this automated actually neural architecture search or hyperparameter search. Okay, there's many methods, GA, GP, PSO, all used in this area. Another area is actually not actually neural network based. That's others. Typical example would be GP based and deep learning. Okay, this include actually automatic region detection, that's low level features, and then from the automatically detected regions, we extract low level features, local regions, right? And then from the low level features, we construct high level features, and then using the high level features for classification. A good thing is that actually interpretation, understandability is much better. Actually, I have to say, and Professor Risto and from University of Texas said that EC is actually deep learning. Previously, I claimed EC is doing deep learning. Risto claimed that EC is deep learning. Okay, and his argument has been published on actually the Seeger Evolution magazine actually, and in 2019 you can have a look. I know the timing is an issue. I'll quickly go through some typical examples to show you some concrete evolutionary machine learning method. The first one I would like to show you is we call Evolutionary. We use genetic algorithm to automatically learn CNNs. We use a variable length representation and proposed and specialized and crossover operator and using very small number of training epochs within each generation. This has been published and attribute transactional evolution computation. Currently, this is the highly cited paper or hot paper, and this is actually is very good on attribute TEC. There's some details I would omitted that give you some result. The fashion MNIST based data set, you can see that, and our method achieved actually the best result here. And so very good result. This is the best, this is the error rate. This is the average, I have to say, because, traditionally in deep learning, most people only report the best result. However, we know that both stochastic methods like gradient descent or actually evolutionary algorithms, they are stochastic methods. They should really run 30 times and then calculate the mean and standard deviations and then report both mean and best, but they didn't, only that. So you can see if you look at the best and our method using evolutionary using genetic algorithms to automatically learn CNN are better than those VGD, the good method. This is the number of parameters and the number of links or weights in those deep neural networks, and much better than 100 million parameters. There's no way to explain. Of course, I have to say our method also 6 million parameters we can't interpret either, right? But better than 100 million. Here, there's a number of epochs, and so that's some kind of measure. Here, that's with comparison on the MNIST variant dataset. That's a different dataset. You can see that we compared with many the state-of-art methods, including the deep neural networks. You can see that our method only slightly less than this method and better than all other methods. And also you can see here, and this method, this data set is very hard and it's better than all other methods. And you can see, and this is a rectangle one, also achieved very good result. Okay? And here I would like to give you a very typical example using two-tier GP, using this basic structure. And you can see that's using genetic programming, learn and a model, a deep model, relatively deep, not very deep, for face recognition, face classification. You can see that this model can be interpreted, can be understood by humans. Like look at here, this is actually a row, start from here, from this coordinator, the length is actually 12. And from here, you can, this is a line. And here is a circle. This is actually the center, the coordinate of the centers. And 9, I think, I can't remember, is the diameter or radius. That's another circle, right? Circle. Here is a rectangle you can see in the nodes, right? Of course, there's another row there again. And you can see, actually, we can interpret this and achieve very good result. More importantly, if we treat every internal node as a feature, we get those internal nodes, internal features, we fit into a standard machine learning method. So the GP constructed features are still much better than the human features, human extracted features. We know that in face recognition, the eye region and the nose, and they are more important. Actually, GP can automatically detect those regions and extract features for that. And this is another extended work. We have input layer and then region detection, feature extraction, feature construction, then classification. And we can see that using GP learned features can interpret and why. And here that's an example. And this is and the two people do different emotions. Here, use a flexible structure. You can learn this kind of trace, those kind of models, and you can see learn different models, and then those features, extract those features, construct features, support and put it into support vector machines, get very good results. You can see the using GP construct features, and on this data set achieve best result. On this data set, and only slightly worse than that, you can see those and receive very, very good results here. More importantly, and the GP constructed features and can be understood by us. You can see that this is the this basically this data set, right? And it can't be distinguished clearly. Some very the boundaries are not clear. However, using GP construct features, and we can see that the 10 classes would be much better separated. The same as the rectangle feature that's here, this category, this data set. You can see that the distinction between the two classes is not that easy to do. But here, using GP construct features can separate those data clearly and easily. And here, and I just provide some additional emergent topic. Right? Here, this is actually using in the evolutionary machine learning area. There are several other topics. Here, that's evolution transfer learning. And actually, and Professor K.C. Tan, and he's the previous editing chief on attribute transactions on evolution computation at University on Hong Kong Polytechnic University. And he present and a keynote speech in WCCI this year, and actually last year, he called evolutionary transfer optimization. I called that evolutionary transfer learning. It's a slightly different, have big overlap there. There are three major techniques here. One is domain adaptation, and meaning that in the source domain, we have many examples with labels. But in the target domain, and we don't have class labels, only have the instances. If we also have class labels in the target domain, and then it's called generalization. Multitasking learning, this is another relatively new paradigm. Actually, using the single representation, you can solve problems in different tasks. And this has been used in classification, regression, and job shop sharing, and achieved very good result. This is another emergent topic people just started. Okay. A second one would be an evolutionary ensemble learning. The ensemble learning is an important method. Here also people have been just starting, right? Lots more. Another one is AutoML. So automated machine learning is just, we automatically learn models. Actually, genetic programming can play an important role for that. And a number of people have already done that. Here, that's the major challenges and current issues here. Although evolutionary machine learning is a big task, it's a big domain, many applications and many aspects we discussed. However, the theoretical foundations of the analysis is still a challenging area. the computation and computational cost is still very high, and the scalability. If the data set is very big, still a problem. And another major challenge is generalization. It can solve and can achieve very good results on the training set. However, on the unseen test set or another domain, and the generalization ability is not good. That people you can still continue to do in this area. In fact, I received a master grant and in this working in this area. Another important area is the interpretability or its explainability. Okay, this is I just show you some examples. Using genetic programming, we can explain easily. However, using traditional like neural networks, that's not going to be possible to interpret anyway. Major applications. I have seen evolutionary machine learning widely used applied to real-world problems. Okay? Here I give you some examples: agriculture or aquaculture, industry and manufacturing, power and energy, and networking, Wi-Fi, internet, and also finance, the stock market, environment, law, this is ethics area, or health, medical, a lot of areas. Instead of drawing a conclusion, I would like to provide some perspectives, right? In my opinion, evolutionary machine learning has become a main direction for machine learning already. If you look at EGKI, Triple AI, the major international conferences and journals in AI, this evolutionary machine learning will become a major direction of machine learning and a focus in the next 5 to 10 years. And so basically, this is not my own view. Professor Zhihua Zhou also has this view, actually. He presented his work in Triple AI and EGKI. So evolutionary machine learning will have a much bigger weighting in EC than now, right? Also, I mentioned earlier, generalization, scalability, interpretability will become the major challenges, but that would be a lot of research. And also, I would expect evolutionary machine learning will be more widely applied to all areas of economics, environment, health outcome, and our daily life. Okay, and of course that's military defense, which I don't like. I don't want to talk about that. And we are close, and we are basically toward the end. This is just a brief introduction of our research group. This is our artificial intelligence and evolutionary computation research group. Has about over 50 people. This is an interdisciplinary area that's computer science, open research, software engineering, electronic engineering, statistics, biology. There's a lot of areas. You can have a look. And we have, like I said, over 50 people, and we have more than 20 academic staff members, have over 30 PhD students. This is some group photos of our group. That's 35 or 40 people. And that's another group. This is our main research directions, strategic directions. When I say strategic, meaning that we are playing international leadership roles in those areas. But the green area, they are big AI, big machine learning. So I'm not making claim on that. This is our recent research grant. And last year, we obtained actually $16 million and for evolutionary machine learning. Actually, on aquaculture, on the fish and shellfish and fillet fish. This $3 million used for the capital city Wellington forest, the trees. Okay, and Marston found a fundamental research. Basically, our group received over 2/3 of the old Marston grant in AI and machine learning in New Zealand. And we also have those and research grants on robotics and agriculture. And here, again, this is the seafood, the cybermarine is big. We received actually recently and 2 months ago. And we also have the, this is actually medical diagnosis in this domain. Finally, I would like to thank Professor Paramasa and also the Calcutta chapter for their invitation for me, and also would like to thank our group of people. Actually, the work I presented clearly not done by myself, right? I think this is the end of this talk. I'm happy to answer any questions. Thank you very much.
Thank you, Minji. Thank you. Hello, can you hear me?
Yes, thank you.
Thank you very much. Some question answer may be there. Please let us see. Devaditya?
Yes, sir. So thank you, Professor Minji, to deliver this wonderful lecture. So participants, if you have any questions, you may ask directly or you may type your question in the chat box. I will read it out.
Okay, I'm happy to answer any questions if you have or any other people have, or you can type in the chat if you like.
So, Professor Minji, can you hear me?
Yes.
I'm Jyoti Prakash Singh. So, thank you for your nice talk. I was just going through that feature selection using the genetic, the evolutionary and this evolutionary computations. So how this, there was one hybrid scheme. One was active, and then there was a filtering, and then wrapper, and then hybrid scheme, combined approaches. So how this hybrid is being done? Can you elaborate on that a bit?
Oh, actually, thanks for your question. This is a good question, actually. Actually, in general, we either use wrapper if we want to improve the accuracy, or actually, if we want to the time efficiency, we use filter approaches. And combining them is not an easy job, actually. And basically, and people have used, I have seen one of my students did actually, but other people have also done that actually. They use some part, and they have a special encoding scheme, and one part and can be used by the like a wrapper classifier, like a nearest neighbor. The other part actually, like they use some of the statistical measures, like correlation measure or distance measure, using simple ones. So trying to take the advantages of both wrapper and filter approaches. And of course, this is need some there are some tricks, need some kind of thought in the design stage. Thank you.
Thank you. Thank you so much.
Any other questions?
I think I can see one question in the chat box. In case of multi-objective scenario, how will EML algorithm will play it out?
Okay, thank you very much. And today I didn't prepare any slides for that, but actually evolutionary multi-objective optimization is one of the major features in evolutionary computation or evolutionary learning. This is actually meaning that, and we want to achieve multiple and conflicting, let me see chat, and multiple conflicting objectives simultaneously. For example, right, in feature selection problems, we want to select a small set of features so that we can understand, we can achieve the interpretability. And meanwhile, we want to actually also achieve a high classification accuracy. So in those areas, they are potentially conflicting. And currently, and any other AI or machine learning programs cannot solve this problem easily, but our evolutionary computation method can use actually multi-objective optimization method and to solve two or more and potentially conflicting objectives simultaneously. Typical examples would include actually like ASGA2 and OSPIA2 or MEOD. Actually, today I didn't prepare for that. I have also have a set distinguished lecture on evolutionary and multi-objective optimization for machine learning and combinatorial optimization. In that talk, actually, I provided a lot of examples on how to use evolutionary multi-objective optimization for machine learning and for combinatorial optimizations and solve multiple and potentially conflicting objectives simultaneously. Thanks.
Thank you, Professor. I think there is one more question in the chat box. I would like to ask that can the feature selection be deployed for denoising and decluttering the noisy data streamed from social networks?
Thanks, that question. That's a good question too, actually. Myself haven't done that. However, I have seen one paper done by other people. I think in social networks, and this is complex networks and social networks. Some people have done that, and but I myself haven't done that. And feature selection, basically, if you have hundreds or thousand features, of course, if you only have 10 features, you can still do probably, and the urgency is not that big, right? But if you have thousands or tens of thousands features, I have millions of features in a IEEE computational intelligence magazine, and they can only find a few features or 20 features. Actually, I have worked on the biomedical data, that biomarker detection. They have over 60,000 features, but only have a very small number of instances. Our method only found actually 13 important biomarkers, actually that features, that can achieve almost 100% of accuracy in a medical diagnosis. So, but the biological or medical doctors, they think that our methods are correct. So that's very noisy. And they have over 60,000 features, but our method can do. So, I believe, and so I have seen other people have done on the social networks, but I myself haven't done that yet. Thanks.
Thank you, Professor. I think there is, if we have time, there is one more question chatted. So if you have time, can you also see that?
No problem. I'm happy to answer. Yeah.
So the question goes on. Biologically, 0% and 100% mutation is not possible, but mathematically it's possible. Then how can we think that GA is good for optimization problem?
Thanks for that question. Actually, this is a fundamental question on genetic algorithms or the whole evolutionary learning area. And in fact, GA, genetic algorithms or genetic programming, clearly they use a mixture of actually crossover and mutation, and also some other recombination method. And of course, biologically, and they can, from the human biology, people, mutation 100% is possible. But in evolutionary computation, that's also possible. And like an evolutionary strategy, and let me see here, evolutionary strategy and evolution programming, and in this page, and they are also based on mutation. I have also seen some of the deep learning methods, and they also use mutation only without crossover. So I think those are all possible. And so it's so we are not following the, yes, it is true that evolution computation are following biology's idea, but we have already become computer algorithms. So pure 100% mutation is actually possible. People have been using that. So this is not a problem. Thank you.
Thank you, Professor Devaditto.
Yeah, thank you, Jyotira. Now
Thank you, Professor, for such an elaborate session on evolutionary computation. It's really very important that we could have figured out the challenges. And one challenge that I found, that is interpretability. Dear Professor, I do agree with you. That is the one problem with machine learning, that is interpretability of the data. And if the data is linguistic and literary one, it is really a challenging thing for machine learning. I think you have already figured out that challenge. Professor, any idea that how to circumvent that particular challenge with reference to literary data, especially?
Yeah.
If you could put light on that.
Yeah, that's an important question. The interpretability has been,
yes,
and make people actually think very, very hard. It's always a hard problem. And however, and this is particularly in the neural network, deep neural networks, hundreds or thousands of layers. Each layer has thousands of feature maps. That's not going to be possible to understand. But actually, in practice, and majority of the problems, or even very hard problems, do not actually need so many layers, in fact.
Yes,
so,
especially the semantic layers. That is one challenging thing with that.
Yeah, but I thought, in my experience, like this example, and like in this example, and you can see that, we can learn some of the using genetic programming, because using using the neural networks, what we do is that we assume, we analyze the distribution. We assume actually we need so many layers, and and then train the parameters. But actually, if we can allow some algorithm like genetic programming to automatically learn those features, learn those layers like here and like that, and then I think this problem can be partially and addressed. Of course, it cannot be, if the genetic programming can also have 20 or 30 layers, it's harder to interpret, but at least it's much better than 300 or 3,000 layers. So you can see many of those stuff, actually they can interpret in some way, right? So, and I think, of course, in this area, people still need to do a lot of work. Yeah, thank you.
Thank you, Professor.
Thank you, Professor Zhang. Now I would like to ask Dr. Indrajit Pant, who is also Vice Chairman of IEEE CIS Kolkata chapter, to deliver both of them.
Thank you, Devaditto. Hope I'm audible. Very good afternoon, and thank you, Professor M.Zhang, for this wonderful lecture. This has unfolded a new dimension of research challenges, and potential applications. I hope the participants and we all have been benefited with this nice lecture on this Sunday morning. And I would also like to thank all the participants for joining us and making this third event successful in this year. I would also like to extend my heartfelt thanks to IEEE Kolkata section for extending their support. And obviously, I must say now that the third distinguished lecture series organized by IEEE CIS Kolkata chapter in 2021 has been going to be a successful one. And in future endeavors, obviously, we'll be looking the same support from all the participants and professors present here. And as long as the pandemic going on, we have to organize this event on a virtual mode. And I believe that once this pandemic will be over, we'll be surely having Professor M.Zhang physically present over here in Kolkata in some occasions, and we will get more opportunity to intensely interact with him, and that will be our fine enough. So with this, I would like to conclude this my short vote of thanks.
Thank you, indeed. Thank you, everybody. Participants, please fill up the feedback form which has been posted in the chat box.
Hello, thank you, Menji, for being with us. So, someday we shall be meeting in person, okay? Let the pandemic be over. Okay.
Yeah.
Thank you. Thank you for your
Thank you. Bye-bye.
cooperation. Bye. Bye.